Hey, welcome back, everyone. It's my pleasure to introduce Matteo Galdiano from University of Hertfordshire, who will speak to us today about the heterotic G2 system with reducible characteristic holonomy. So, Matteo, please.
Yeah, thank you very much, Jeff. And yeah, I want to thank the organizers for the opportunity to give this talk and in general for putting together this seminar series, which, yeah, I'm very excited about it. So thanks all for organizing all this. I think there's a very nice lineup of speakers. I guess I'm biased, but yeah, I do. I'm very excited about this. So yeah, I'm also very excited to tell you a bit about this work that I did with Leander Stecker a couple of years ago at this point, but it was published only recently. So I'd like to start the talk by giving you a one-slide summary, something that I like to do. So yeah, if you just pay attention for the next minute or so, you can get at least the main points of this talk, and you can decide if you want to keep paying attention. And I'll do it in this format of these five W's and H that I like. So, these five W's, first is who and when. I already told you this project I did with Leander Stecker, was a postdoc at Hamburg at the time with me. We were both postdocs, and we were sitting in front of each other. So it was a very nice collaborative effort that we did. And yeah, we published this 2 months ago, very recently. So what is the that we study? What is the thing that I'm going to be telling you about? Well, we study something called the heterotic G2 system. Essentially, it's a system of equations that describes compactifications of heterotic supergravity on 7-dimensional manifolds. So it's a 7-dimensional analog of the Hall-Strominger system that perhaps you're more familiar with. But of course, I'll give you more details about this during the talk. Now, where do we study it? Well, we focus on what are called 3 alpha delta Sasaki manifolds, which are some generalizations of 3 Sasaki manifolds. And actually, you can think of them a bit as an odd analog of hyperkähler manifolds or hyperhermitian manifolds. So it's very similar to what Beatrice was talking about last week. You'll see that there's a lot of connections. Now, perhaps the more interesting thing is how do we study this? How do we actually study the system? Well, we actually rely on some reduced structure that these manifolds have. And we're going to have to choose some connections that have some good properties adapted to this structure to be able to solve this complicated system of equations. And yeah, perhaps the most interesting question is, why do we study this? Why do we care about this? And for this, it's actually an interesting problem for both strings and geometry, which I think makes it very interesting for a string geometry seminar. So it has some physical interest. It provides some supergravity solutions, but also it's a bit of it has some very interesting geometry underlying it that even if you're a mathematician and you don't care about string theory, I think you'll find very exciting. At least I do. So now, for what I'm going to be telling you about, the plan of the talk, I'm going to tell you, I want to start with some more introduction and motivation, and then I'll just go over essentially what I've just summarized for you. I'll define for you this heterotic G2 system, which is what the object of study. I'll explain to you how I want to look at this reduced G2 structure that we have there and how some holonomies of some connections reduce. I'll present to you these 3 alpha delta Sasaki manifolds that I guess maybe there's a considerable number of you who haven't seen this before. So it will be hopefully some interesting geometry. And I'll explain how to build some G2 instantons on these cases, and then I'll present some new solutions that we found before concluding. So for the, and of course, please interrupt me anytime. Feel free to ask questions. It's okay if I don't go over every single slide that I have. I'd rather make sure that all of you are following and understanding. And yeah. For the introduction and motivation, I wanted to do a bit of an extended introduction because I feel like just looking at the talks that we're going to be having this seminar and so on, there's a lot of these geometries motivated by string theory. And since I have some like a big string theory background, I felt like I wanted to talk a bit about why these things arise from string theory. So please bear with me if you are very mathematically focused. But I think it's interesting if you've never heard about this before to see it once, so that some things might click in your brain and some of these buzzwords, you understand them a bit better. So what is supergravity? Supergravity is the gauge theory of local supersymmetry. Okay, but this is not how I like to think about this. Also, people always say that it arises as the low energy limit of string theory, but you don't need to understand what is a low energy limit of anything to get a grasp of what supergravity. Really, how I like to think of supergravity theories is just some of them being described by an action, something very common that we're all very familiar with. And here's an example of an action, supergravity action, that you can think of as a generalization of the Einstein-Hilbert action, right? Instead of just the Ricci scalar, you have some other term. And what happens in supergravity is that your field content, your bosonic field content, has some extra things. Not only you have a metric, but you can have, for example, a three-form H. This is three-form flux. You can have a scalar field known as the dilaton. In our case, because it is heterotic setting, we'll have also some additional gauge fields on some bundles over our manifold. For the rest of the talk, by the way, I'm going to try to highlight in blue things related to geometry, and in green things related to gauge fields and connections. So there's a bit of a color code to guide you a bit through the slides as well. So now, what happens when you have an action? You always like to compute the equations of motion. So the task that you might want to do is to find some field configurations that solve these equations of motion. And this is hard in general. So because we want to make our life easier, we like to throw in some extra assumptions. And these are some very typical things that you might want to assume. One of them is this compactification ansatz, which is assuming that because we are doing string theory, we have some 10-dimensional space, but we're going to think that we have a direct product, or sometimes a word product, some kind of product, where there's what is called some space-time part, where the Lorentzian geometry is there, and then some compact manifold. And essentially what we're going to do is focus on this compact manifold part and think of our problem as Riemannian, which is not something that you have to do. You can also focus on this Lorentzian part. And I think I saw Marco Fibers giving a talk in a couple of weeks, and he will talk more about the Lorentzian nature of things. But in this talk, let's focus just on the Riemannian part. There's also some other technical assumptions. You set some parametric background close to 0, just that you have less things to worry about. But crucially, the crucial assumption is that you assume that you're preserving some supersymmetry. And the moment you have supersymmetry, it means that you have some well-defined spinors on your manifold. And then you have all these tools of spinor geometry that come to help you and help you solve your problem. In particular, you get this physics just tells you that you have to satisfy something called the Killing spinor equations, which are some equations that are first order instead of second order. So let me show you an example. So these are an example of Killing spinor equations. The form is not super important. I'll walk you a bit through it. But the key idea is that these Killing spinor equations are easier to solve than the equations of motion. And in some cases, if you make some assumptions, they're actually not. You can see that you solve them. So these are typically spinorial equations. Here epsilon is a spinor. So they immediately are telling you things about the geometry of your manifold. So you see, just by assuming this supersymmetry and imposing some kind of physical conditions, suddenly you're in the realm of differential geometry. And, if you look at the equations, for example, this first one is the Gravitino equation. It just tells you that you have some G structure on your manifold. For example, a way you can understand this or see in an easy case is assume this H is 0. This is just saying that you have some spinor that is preserved by your Levi beta connection. You have some covariantly constant spinor, and you are immediately in the realm of a lot of special oronic manifolds that we all know and love. But because we're going to be doing physics that are a bit more complicated, we have this extra term that is going to add some torsion. Hence the geometries with torsion that arise here from physics. And yeah, different equations impose other conditions. In our case, because it's heterotic setting, you have also this extra gauge field. And the supersymmetry condition tells you that you need to have a G instantons. We're going to have a bit of instanton connections as well. So see topics that are very familiar in differential geometry, but here they appear very naturally from physics. And this is a very general system that you can study it in different dimensions. And when you do this for 6 dimensions, you get the whole Strominger system. But we're going to do it for 7 dimensions. We're going to get a 7-dimensional analog. And we want to reinterpret this physical system in terms of geometrical data, in terms of geometry. And once you've done that, if you want, you can forget about the physics and just solve a problem in differential geometry, which can be interesting on its own. But if you remember that it comes from physics, you might actually be able to say some interesting things about the physics behind it, which I think is very cool as well. So let's do a bit of that. So what is our subject of study in this talk? We are going to study heterotic supergravity, just some particular type of supergravity. We're going to look at 7-dimensional manifolds. So in this sense that we take a 7-dimensional compact manifold, which means that our spacetime is going to be either Minkowski or anti-de Sitter in 3 dimensions. And we are going to demand this minimal supersymmetry. Now, there's a lot of references and work in this direction, both by physicists and mathematicians. And the thing about this particular setup I'm choosing is that even though there's been a bunch of work, these compactifications remain a bit mysterious. I always give the example that this possibility of having this anti-de Sitter spacetime went unnoticed for many years. So even though it's a very interesting problem, I think there's still a lot to be learned. And explicit solutions to this system of equations are actually very scarce in the literature. Here I'll talk a bit later about some of these solutions. I also recently, Viviana Del Barco told me that they had some new solutions. So hopefully soon there will be another reference here. There was a paper on the arXiv today about solutions to this system precisely. So it's an interesting topic, and I think everyone's welcome to come and find solutions because there's just so little that we know about this that any solution is welcome. And yeah, for the more mathematically inclined, big motivation to study this is the rich mathematical structure of this system of equations. So it's a very natural playground to deal with G2 geometry and G2 instantons, because they just pop up from the equations naturally. But there's much more to be studied here. There's a whole, people have been looking at the deformation theory and the modular spaces of these solutions and how do they work. It connects with spinor geometry, as I said, and with generalized geometry. This system can all be rephrased using generalized geometry. So it touches on many aspects of differential geometry. And there's also some more like physics motivated reasons to look at this, because you have these anti-de Sitter backgrounds. You might wonder if there's some heterotic version of holography for these solutions. It's something that people haven't thought much about. Or what happens with these ADS-Swampland conjectures in this setting, that you might have heard these Swampland buzzwords. Well, if we have more solutions of this type, maybe we're able to say something about this. That will be very interesting. Okay, now let me tell you a bit more about what is this heterotic G2 system, and I want to tell you a bit about the ingredients that we need. So if you have what is called an N=1 vacuum solution of this heterotic G2 system, essentially to find this solution, you need the following ingredients. One is just a compact manifold with an integrable G2 structure. I'll explain a bit like the little adjectives and things that I've been throwing in here. But you need also a couple of connections, one in a vector bundle and another one in a tangent bundle, and they have to be G2 instantons with respect to this G2 structure. And you also need this 3-form flux field, which is just set by the torsion of the G2 structure. That's why I put them in the same color, because this is kind of the geometry part of the thing. But the magic of this system comes from this equation. This is called the heterotic Bianchi identity. And what it's doing is coupling the G2 structure, which enters through here, with these connections in these bundles, because otherwise they would be just independently, but this additional condition couples them together, and is what the meat of the problem is and what makes it hard to find solutions. Here, this alpha prime is just a constant positive parameter, like a physical parameter measuring the length of your string, but you don't have to worry too much about that. It's just a parameter. So essentially, if you want to give me a solution to this heterotic G2 system, you have to give me this quadruple with the manifold, the connections, the flux, and then you have to ensure that you satisfy this. Very good. So
Sorry,
now,
Mateo.
yes, please.
I mean, the H is like this canonical H, right? This is the torsion of the, so it's not really a
Yes.
separate
Yes,
object,
yes, I agree. And this is true. H is fixed to be the torsion, the characteristic torsion of your G2 structure. So yeah, once you set the G2 structure, H is defined. Yeah, I guess I'm just adding it here as a reminder that we're gonna need it to satisfy this extra condition if you want. But yeah, that's a very good point. Thank you. Good. Well, oh yes. So now let me actually walk you a bit through these definitions so that we are all on the same page. I know that some of you have probably, well, I think it's a bit embarrassing that I'm saying G2 structures to some of you people in the audience, but I should still do it, I think. So we are all in the same page and we are all using the same notation. Let me just say a bit about G2 structures. Also, how do I think about them and what is interesting for the purpose of this talk. So a G2 structure on your manifold, 7-dimensional manifold, it's a reduction of the structural group of the frame bundle of the manifold to G2. But the way I think about it is in terms of form. So this is equivalent to the existence of a non-degenerate positive 3 form on the manifold, which is called the associative 3 form. And if these adjectives don't tell anything to you, the important thing to keep in mind is that this 3 form that we have defined all over the manifold, locally, we can always bring it to this form for some orthonormal basis of 1, the manifold, okay? So G2 structure, we have these 3 forms. Good. But this 3 form immediately comes with some extra perks. From this 3 form, we can immediately construct a metric. There's some formula to do this. There's a Hodge star as well, which gives us this co-associative 4 form, the Hodge star of phi, which we call psi. So we have these 2 tensors, phi and psi, on our manifold. And another consequence of having a G2 structure is that any tensors that you have in your manifold, now you can further decompose them into G2 representations. So for example, if you have the space of 2 forms, now it splits into a 7-dimensional and a 14-dimensional part. That's what I'm representing with these numbers. And these subspaces are defined in terms of the R forms. For example, the 14-dimensional part are those 2 forms that satisfy this condition. And actually, this part will be very important because it can be identified with the algebra of G2. But the important thing is that we can always split everything in G2 representations. And this is very interesting because now some of you might be more familiar with the concept of G2 holonomy manifolds. And G2 holonomy just means that you have a G2 structure, as I explained above, but the 3 form and the 4 form are closed, both of them. This is a general definition of G2 holonomy. G2 holonomy, as you might know, it's very, very restrictive. It's very hard to construct compact manifolds with G2 holonomy. But luckily, actually, the physics that we're going to be looking into, what they want a G2 structure with torsion, which is what I'm going to define now for you. So it's something much more general than G2 holonomy and actually much more ubiquitous. That you can find it essentially any 7-dimensional manifold that has like it's orientable and spin has one of these G2 structures. So there's many options. So yeah, what I mean by a general G2 structure is the case where these 3 form and 4 form are not closed. So they can be anything. And if you decompose everything into G2 representations, you can always write it in this form. So here I'm introducing these tau k's, which are k-forms called torsion classes. And the way you should think about this, if you have never seen it before, is that these k-forms tell you kind of what type of geometry do you have in here, and tell you a lot of properties about the G2 structure that you have. They have to belong to certain representations. This is not super important. So now that we have defined what a G2 structure is and we've seen these torsion classes, if you remember, these Killing-Spinor equations were imposing certain conditions in our geometry. In particular, we're going to need a special type of G2 structure. And these are called integrable G2 structures. So a G2 structure is called integrable if this torsion class, tau2, is equal to 0. So in that case, if you see before I had this tau2 here, now I'm going to look at cases where this tau2 is equal to 0. So what's interesting about this type of G2 structures? Well, for them, they admit a distinguished connection that I'm going to be calling characteristic connection, which is a connection with totally antisymmetric torsion, and it's encoded by this formula. So it really depends only on your G2 structure and your torsion classes. And this is the torsion of the G2 structure. And as Jeff was pointing out earlier, this is actually going to be identified with this physical flux, with one of the fields in our theory. So this is a very important quantity. And actually, now I'm mentioning physics, let me tell you a bit about the implications that this has for physics, because interestingly, a lot of interesting physical quantities are encoded by this torsion class of the G2 structure. So if I have a solution of this heterotic G2 system on some G2 manifold, and I know these torsion classes, actually I know a lot about the physics that is underlying my solution. For example, the cosmological constant of this three-dimensional spacetime, the curvature of this three-dimensional spacetime, if you want, is proportional to this torsion class tau0, which is a scalar number. So it so happens that if tau0 is equal to 0, your spacetime is Minkowski. Otherwise, you have some anti-de Sitter spacetime. So you see, just out of computing this G2 structure, you get some information about your three-dimensional universe. It's very remarkable. Yeah, and the physical fields are also determined by the torsion classes. For example, the dilaton is essentially set by this tau1. And as we mentioned earlier, the three-form flux has to be identified with this torsion. This is something that the Killing-Spinor equations tell you. So you cannot run away from it. So I think this is a cool thing. It's a nice interaction between strings and geometry. Like your geometry is telling you something about the background where your strings are living. Okay, we have to remember that there's not just this geometry part. There were also these connections in this system, right? These gauge fields. And the condition that these gauge fields must satisfy is that they have to be G2 instantons. So what does it mean to be a G2 instanton? It just means that the curvature of your connection lies in a very particular space. So usually you can think of a curvature of a connection as a true form taking values in the endomorphism, so the vector bundle. What we ask is that rather than taking values in the whole true form, it takes values in this particular part of the true form that is identified with the Lie algebra. So this G2 instanton condition is a restriction on the true form part of the curvature. And you can rephrase it in terms of this form of the G2 structure. Maybe at this point I should say, in case you are more familiar with complex geometry, that this is, or like maybe to make a connection also with the talk last week, that this kind of the G2 analog of Hermitian-Yang-Mills, the condition of Hermitian-Yang-Mills for a connection, something very similar. And in the same way, you know, a G2 structure is also like a seven-dimensional type of geometry that is similar to a Taylor thing. You also have some distinguished forms, and they satisfy some geometrical properties. But anyway, I'll say a bit more about connections between G2 and hyperkähler with torsion stuff a bit later. Yeah, sorry. And as I insisted already earlier, the heterotic Bianchi identity is particularly hard to solve, and it's where the meat of the problem is. So we're going to need to construct some G2 manifolds that are interesting, try to find G2 instantons, and try to satisfy this equation. This is what we're going to try to do. So we are not the first people to do this. There are previous solutions in the literature. Here I'm just listing how they look like. Some solutions were constructed in flat space, and the first compact solutions came actually much later. You see by Fernandez, Ivanov, Ugarte, Villacampa, and Vasilev, and they were of the form of a product, a six-dimensional manifold and a circle, some nil manifolds. A bit later, Clark, Garcia, Fernandez, and Tipler constructed some collection of families as T3 bundles over K3 surfaces. And then Jason Lotte and Rick Saer constructed the first ADS3 solution using contact Calabi-Yau manifold. And then together with Xenia on my PhD thesis, we also looked at ADS3 solutions using some homogeneous three-Sasaki manifolds. And as I was mentioning, yeah, there are some, I know that Viviana del Barco and Andres Moreno and Clark, I think, they also have some new solutions. So we'll have to add them to the list very soon.
Actually, Matteo,
yes.
For any of these examples, by any chance, did they turn the gauge bundle off for any of these examples?
Right, that is a good question. So if I remember correctly, so there are some cases where maybe, the way I'm presenting it, there are two connections on a connection on the gauge bundle, a connection on the tangent bundle. I think there are some of these solutions where one of them is turned off.
Yeah, sorry, I think I meant more that the sort of tangent bundle piece was ignored. That's actually
right.
What I meant.
The whole part. So what happens if you turn off that gauge bundle part, which you can do, is that suddenly you are in a case where your torsion has to be closed, right? You're in the case of closed torsion.
Yeah.
Essentially because, if you turn off this part, you just have DH equal to 0, which is perfectly fine. But then at this moment, you are kind of decoupling these gauge bundles, and so this heterotic part is decoupled, and you're just looking at what is called the common sector of the type 2 aneterotic theories. And then when you do that is absolutely fine. Then you end up in all these kind of geometries that have to be like pluriclosed, or like it will be like the analog of that, things where you have like the DH equal to 0. And I think these solutions I'm listing here, maybe, I think in most of them, they don't do it. Just because, just to keep so it's just that you solve a different problem if you do it. You're kind of completely decoupling the gauge bundle, and you're solving a different type of system, and typically with more supersymmetry, actually, which is absolutely fine. And you can do it, and in the literature, there's a lot of solutions. I think a lot of people have studied the thing with H closed, even in the G2 case. But for what we were interested in is in actually trying to not turn this and make it non-trivial. But if I remember correctly, for the ones I list here, I think all of them have the gauge field, or some of the gauge fields non-zero.
Okay, yeah, thanks.
Yeah.
Sorry, maybe a related question. So if you go back to the heterotic Bianchi identity, do you physically expect that the theta is like? I vaguely remember that can't you regard theta as like like what do I want to say? Sorry, like the metric ametric connection with torsion, so it's kind of determined by the rest of the data somehow.
Right. Yes. So so this connection, it depends. So there are a couple of different schools of thought on how you interpret this. If you want to more follow like the hardcore physics approach, or like you want to be more of a mathematician, because, well, I don't know, maybe I'm oversimplifying things here, but it is true that if you try to follow these things like order by order in perturbation theory, in string theory, and so on,
Mm-hmm.
If you do this order by order, this theta equation is kind of fixed order by order, and in some cases, this theta is actually determined to be one particular connection. So
Mm-hmm.
in the Hall-Strominger system, for example, it so happens that it has to be not the bismuth connection as in the other one, so the other side.
I see, but it's like the one which is metric but with prescribed torsion, right?
Yeah, so this happens sometimes. I have to say, in my approach, the way I look at this, I don't fix the connection theta, and instead I use a theorem by Friedrich, I think was the one who that tells you that, because in the end, I'm solving the Killing-Spinor equations, and eventually solving the Killing-Spinor equations is good, but you would like physically to solve the equations of motion of your theory, right? So the Killing-Spinor equations usually are not enough to solve the equations of motion. You have to add a little bit on top. So there's a theorem by Friedrich that if you add this heterodyne identity and you ask this theta to be an instanton, then it is enough and you solve the equations of motion. So that's my motivation to consider this theta to be an instanton rather than to worry about the, So I'm kind of a bit forgetting about this order by order perturbation theory thing. And at this point, I'm treating this as a specific problem where these connections are arbitrary. And then, there's a theorem that tells you that when this is an instanton, then you solve the equations of motion. And that's kind of what I want to do. So that's why I choose it like this. But the literature is a bit confusing in this regard sometimes. When you look at different people, they make different choices. Then solving this exactly is very hard. So you can also invoke physics and say, okay, maybe I have to solve this up to order alpha prime squared, and then which connection you have to choose. It can be a bit confusing, but in some sense, So it's a very good question, actually. And even though I've worked on this for a while, sometimes I'm confused about it myself.
Thanks. That was very helpful. Thanks.
Yeah, thank you. It's a very good question, actually. Okay. There are no more questions. Then I just want to point out before we move on that if you look at the type of solutions that we see here, actually the ones that appear today on the arXiv are also T3 bundles over K3. If you look at this, you'll see that all of them are they have a bit of a reduced structure, right, in some sense. They are like these products or bundles, this contact clavio. There's always a bit more going on. So this was a bit our motivation to look in this project a bit more at what's happening, because all these solutions have some kind of reduced structure to them. And it's true that when you have a G2 structure, you always have some topological reduction to SU3 and SU2 structures using contact geometry. So we wanted to see if we could find new solutions using this perspective, trying to reduce the structure. And, if you look at these inclusions, G2, SU3, SU2, there's this SP1, SP1 sitting here. And in this talk, I'm going to focus on this SP1, SP1, because what we observe is that when the autonomy of your connection motivated the connection, this characteristic connection associated to the G2 structure, if the autonomy reduces here, then we actually have some tools to solve this heterotic G2 system. So let me, Joshua, you have a question? I cannot hear you. Can you hear me? I cannot hear you. But...
Yeah, I think we aren't hearing you.
Yeah, we still can't hear you.
We still
can't. I cannot hear you. Oh no. Feel free to type otherwise.
Yeah, maybe go ahead. I don't know.
But well, okay, I'll go ahead. But please do ask me your question later. So yeah, what I was saying is that this is what we're going to look into. So how we're going to reduce the G2 structure in some sense? Well, I was kind of telling you earlier that there's some easy examples that maybe can guide us a little bit. So if you've seen some G2 structures, you've seen that the first two examples that people give you is that if you have a 6-dimensional manifold and you take product with a circle, and your 6-dimensional manifold has an SU3 structure with an Hermitian form and a holomorphic volume form, then you can build a G2 structure like this. And if you have something that is 4-dimensional with an SU2 structure, then you take a product with 3 circles and you can build a G2 structure like this. So how do you do this for more complicated manifolds? Well, this is where contact geometry comes to help you a little bit. So I want to talk a little bit about contact geometry to motivate the manifolds we're going to look into. So what are these contact structures in 2n+1 dimensions? You can think of them as odd-dimensional analogs of scalar structures. So what is an almost contact structure? It's like just a tuple of a vector field, a 1 form, and a 1-1 tensor field satisfying these identities. So what is this doing? It just tells you that this 1-1 tensor field squares 2 minus the identity in the part that is orthogonal to this vector field, acts trivially on the vector field, and the 1 form is just a dual of the vector field. So if you think about it, it's just telling you that this phi is kind of like a complex structure on the space that is orthogonal to your vector field. And once you have this, it's easy to see that you have some compatible metric G, compatible in the obvious sense of the definition here. And you can define a fundamental form in this way. And this is the analog of the Hermitian form. So you see that it's like an odd-dimensional Hermitian manifold in some sense. Okay, so this is a very natural way of thinking how you go from an odd-dimensional thing to a more familiar even-dimensional structure. So now you can ask a bit more to make things easier to study. And you have an almost contact metric structure, as I defined above. You say that it's alpha Sasaki if the exterior derivative of this 1 form is related to this fundamental form that I was defining here. So it's a relation between the eta and the phi, if you want. And there's an extra technical condition that we worry about. And these are what are called alpha Sasaki manifolds. And you might have heard that the cone over a Sasaki manifold, alpha 1, is scalar. And you could think of these manifolds as some circle bundles over Kähler orbitals. So that also stresses more how these are odd-dimensional cousins of Kähler orbitals. And in 7 dimensions, you know, if the base orbital has an SU3 structure, we can obtain a G2 structure precisely as we were saying earlier for the direct product. But now you have a circle bundle that is a bit more interesting. So this is the case that we want to build upon. And a very natural thing, if you have Kähler, you can go to hyperkähler. Here you can do exactly the same thing. And you can define 3 contact structures, which are the odd-dimensional analogs of hyperkähler structures. So now how does this work? You have 3 different almost contact structures, and you make them play together like the quaternions. So this is really like an odd-dimensional version of these hyperhermitian geometries that Beatrice was talking about last week, if you were around. And now you have your tangent bundle has an horizontal part and a vertical part with these 3 Reeve vector fields. And again, you have the fundamental forms. And again, you can define this, what it means to be 3 alpha Sasaki by imposing that each of the 1 forms and fundamental 2 forms are related. And the cone over a 3 Sasaki manifold is hyperkähler. So you see that these are honestly like some odd-dimensional cousins of hyperkähler geometry or hyperhermitian geometry. And these are kind of SU2 bundles over quaternionic Kähler orbits. It's another way to think about this. And again, in 7 dimensions, we can obtain a G2 structure in an interesting way. Okay, this is very nice. But as I was telling you, well, okay, sorry. I forgot that I include an easy example, of course, because examples are very important. So an easy example is the 7th sphere with the standard metric. It's a Sasaki manifold via the complex Hopf vibration. So you can think of the seventh sphere as a circle bundle over CP3. It's also 3 Sasaki using the quaternionic Hopf vibration. So you can think of the seventh sphere as an SU2 bundle over S4. And now if you take the standard metric and you do some rescaling along the fibers and the base, you can actually obtain these alpha Sasaki and 3 alpha Sasaki strands. Okay. So you can just think of a sphere and how you rescale things to have a picture of what kind of spaces I want to deal with. Because now I want to go a bit further. Instead of 3 alpha Sasaki, I want to add this extra letter here, delta. So what are these 3 alpha delta Sasaki manifolds? Well, it's actually something very similar. It's just an almost 3 contact metric manifold, so this analog of hyperemission. But before, for 3 alpha Sasaki, I was just asking for this blue part. Now I add this extra red term, where now alpha is non-zero, but delta can be 0, and these are like real. This was introduced by Agricola and DeLeo. So what is the point of having this thing? Well, notice that first of all, it covers the cases that I was mentioning before. For alpha and delta equals 1, this is just a 3 Sasaki. Actually, for alpha equals delta, this new term just drops off. So it covers 3 alpha Sasaki. But it also covers some interesting cases. For example, when delta is equal to 5 alpha, it was called a squash 3 alpha Sasaki manifold. If you ever encountered this squash 3 Sasaki metrics. So it's kind of, we have this parameter and we cover like a higher ground. And actually, a way to think about these 3 alpha delta Sasaki manifolds is that they are bundles over some quaternionic Keller orbifolds, where the scalar curvature is proportional to alpha delta. So this immediately tells us that there's 2 possibilities. When alpha delta is non-zero, where you have an SU2 bundle, and there's something weird that happens when delta is equal to 0. So, which is that you have an R3 or T3 bundle. So if you look, I'm going to go back for a second. What happens if delta is equal to 0 is that these 2 alpha here kills part of the phi I here. So you are in some kind of degenerate case. And that's why the bundle changes. So interesting that some different topological bundles here.
So, Matteo, that's like a
Yes.
local theorem, this thing in gray? I mean, somehow, isn't it saying they're effectively rigid? I mean, this quaternionic Kähler is already rigid, right?
Right, yes. So I think I didn't phrase it very well, because in case when delta is equal to 0, you are actually not quaternionic Kähler, you are hyperkähler. So it's a bit broader than that. And it's pretty, but yeah, and they are like, you can emit orbitals. So it's like, you can have some singularities and so on. But yeah, I think you might be right. It might be just a local result. Yeah, I will have to check. I'm pretty sure there's some discussion in this paper by Agricola and DeLeo. And probably in this one with Leander, they studied quite a bit this setup. Yeah, I feel like I should be able to answer this question better. But I think you might be right. It might just be like a local statement, a local picture that we should have. Which for me is kind of what I want to have in mind, because I want to solve these equations that I just need to solve them kind of locally sometimes. But yeah, a good question. Yeah, and there's different behaviors of these 3 alpha delta Sasaki manifolds. So when alpha times delta is positive, if, for example, like a 7 sphere would be the case. As I was saying, the delta equals 0 is a degenerate case. An example would be T3 bundles over K3 surfaces. And there's also these negative 3 alpha delta Sasaki that are a bit more exotic. And you can, in this paper, you can have a look and see. But yeah, these are like interesting spaces. And as you can see, we have this space of parameters with the positive, the degenerate and negative 3 alpha delta Sasakis. And 3 Sasaki would be lying here, 3 alpha Sasaki would be a line. But we have kind of expanded our thing. We have this degenerate case. So our hope looking at these spaces would be that we would be able to cover more cases and do a more systematic study of what happens. And one of the reasons why we focus on these 3 alpha delta Saki spaces is that they all come with a G2 structure naturally equipped. And once we have this G2 structure, we can immediately compute the torsion classes, and we can see what's up with these spaces. So this is just a computation that you can do. And you can notice here that tau 0 is always non-zero, and that tau 2 is always 0. So because this tau 2 is equal to 0, we know that they are good for our heterotic G2 system. That makes us very happy. So as I was highlighting earlier, once you have these torsion classes, you can already say a lot of what a compactification, supergravity compactification on these spaces would look like. So as I was saying, they have this integrable G2 structure, it's a closed G2 structure, so it's a bit more. So they are good for the heterotic G2 system. All of them give rise to this ADS3 spacetime. So the tau 0 is non-zero, which is interesting. We have constant dilaton, because tau 1 is equal to 0. And the three-form flux is determined to be this number. So we already know a lot about the physical field just by looking at the geometry. Okay. Now, in some sense, what we have done is we've chosen our G2 structure, which also fixes H, but we still need to choose some G2 instantons over our manifolds and solve this equation. So let's have a look at those G2 instantons, and this hopefully is going to motivate a bit more why these 3 alpha delta spaces are particularly interesting. Essentially, something that happens is that this characteristic G2 connection, so this connection that is prescribed by the G2 structure and has total antisymmetric torsion, when you are in the 3 alpha delta Saki setting, it agrees with something that Agricola and Di Leo call the canonical connection, which is defined to be the unique connection with totally antisymmetric torsion that satisfies this property, where this beta is just a constant. So this property, on a first look, it might not it's not maybe particularly illuminating, but it's actually something that makes sure that this connection is very well behaved with respect to this bundle structure that I was mentioning earlier. So it's somehow it's telling us that this connection is also well adapted to the structure that we have. So the connection preserves the splitting of the bundles in the horizontal and vertical and projects well to this orbifold at the base. And in particular, the curvature is also well behaved. It's something that we want for the to check the G2 instant. I'll say more about this in a second. But perhaps more interestingly, you can show that it is a G2 instanton. And you might want, so this is like kind of very nice. On the nose, this characteristic G2 connection is already a G2 instanton. We wanted a couple of them. We already have one. This is very good. And you can wonder if we can find similar connections. Maybe I should say that secretly, the reason why this is a G2 instanton is because this torsion is parallel with respect to the connection with torsion. So it's a connection with skew torsion that is parallel. And then this means that you have some symmetry in your indices that help you realize that this is a G2 instanton. So I guess this is just to say that this connection in these spaces is very nicely behaved. And this encouraged us to try to find similar connections in here. So what can you do once you have a connection that is well behaved? Well, I think the most natural thing to do is to try to deform it and try to see if you can, how much you can play with your connection, how much wiggle room do you have to find similar stuff. So this is what we did. We took our torsion that we knew worked very nice, and we defined a family of connections just using the G2 structure. And this connection can be motivated from a couple of perspectives. If delta is different from 5 alpha, it agrees with the family of connections that is compatible with the G2 structure, which in this case is a one-parameter family. But you can also think of it as being the canonical connection for a different 3 alpha delta Sasaki, just on the formation of the connection. But the interesting thing is that if you actually pick this guy, all these good properties I was telling you about, the canonical connection, carry over to this family. So you have a very similar property in terms of how this covariant derivative behaves, where now you see there's a dependence on lambda, which is the parameter of the family. And of course, lambda equal to 0 recovers our previous connection. But yeah, it still preserves this splitting in the tangent bundle, projects well to this orbifold, and the curvature has a nice behavior and has this decomposition. So in this decomposition, there is a part, this R2 part, that is purely horizontal. And then there's this R1 part that mixes vertical and horizontal components. Vertical and horizontal meaning components in this sense of this splitting. But this part depends on lambda, and this part doesn't depend on lambda. It's like a universal part that you have in this family. And we will see that this is important later. And somehow this R1 part, you can compute it explicitly, and R2 depends on the orbifold that you have in the base. Okay, so now we can, because we have this control of the curvature, we can study what happens with this instanton condition. And what we encountered, we didn't know what to expect, but it turned out that actually we have a G2 instanton for two different values, lambda equals to 0 or minus beta. Lambda equal to 0 is, of course, the canonical connection, like this, and the one that agrees with the characteristic connection for the G2 manifold. So it's what we had already. But we see that we have this other value in the family. And what is happening in this case is that we are picking a connection such that it acts trivially on the vertical part. And this, for Tridesaki manifold, agrees with what Harlan and Noel call the canonical connection. So yeah, and this you have to be careful sometimes because this canonical connection and this canonical connection are not the same, but they are canonical with respect to different things. So yeah, sometimes it's better to avoid the name canonical because what canonical means for different people is not canonical. But yeah, so we have these two instantons. And recall that we need an instanton connection on the tangent bundle and another instanton connection on some vector bundle. So what we will do is just choose our vector bundle to be the tangent bundle again and try to play with these connections, try to solve the problem. So now we've picked our connections, we have our geometry. What remains to do is look at this heterotic Bianchi identity. So let me tell you what we found. What are the new solutions that we found in this way? We have to impose the heterotic Bianchi identity. And this derivative of the flux, the left-hand side, is determined. This, you have to take your H and apply the exterior derivative. And you can write it in terms of these fundamental forms, the ether that we had before. And this holds for any 3 alpha delta Sasaki manifold. Now, for the right-hand side, these terms you can compute them for our parameter, for our lambda parameter of connections. Right? Our lambda, one parameter family of connections, the parameter lambda. And you have this very nice behavior where, remember I was telling you that the curvature was splitting into R2 and R1 part? Well, it turns out that you have this R2 contribution and then some additional contribution that depends on this form. You see, which are kind of the same that you have here. So now you can just put this in here and try to see if you can find a solution. So these are the main results I'm going to tell you about today, is that we tried different instantons and different configurations. And what we found is that you can actually solve the system in one case. You obtain a solution of the heterotic G2 system by choosing, and this is something that, yeah, we didn't know what to expect. And what we found is that in this way that we're doing it, with these instantons that we're choosing, you only have a solution in the degenerate case, the delta equals 0 case. And you have to pick actually one of each. One instanton that is this minus beta 1, and the one we started with the characteristic G2 connection. And then you can solve the heterotic Bianchi identity, and this parameter is given by alpha. So this is very nice. It's very nice because somehow, you know, this is a very non-trivial equation that you have to satisfy. And the secret here, I'll tell you a bit of the idea of the proof. Well, maybe yes, of course, these are new solutions, which is always very nice. But the reason why it secretly is working in our case is that in the right-hand side of the Bianchi identity, the terms that depend on the base orbifold cancel out. So if you remember here in this expression, you have this contribution, and because we are choosing both terms to be in this one parameter family, this term where we don't have control, actually they cancel out. And we end up only with parts that depend on these forms that we know. And at that point, it becomes an algebraic problem where you can look at the coefficient of these terms and you have some algebraic equations that you try to solve. And in this case, we're lucky and there is some solution. Something that I wanted to mention that, as I was saying earlier, in the literature, sometimes it's a bit confusing. What is the heterotic G2 system even? I just want to say that if you are a bit more relaxed and you say, okay, maybe the connection I want to choose, I don't need to be exactly a G2 instanton. I allow it to be a G2 instanton up to order alpha prime squared. Then you can relax things a little bit because you can use the full family of connections to try to obtain solutions. And you can obtain some, if you want, approximate solutions to a heterotic G2 system. That's something that people have done in the literature as well. But it's interesting that here, even if you are strict and you're like, no, I want the exact thing, you still find some solutions. It's remarkable, I think. And am I doing the time? Okay. So if I have a couple of minutes, I'll tell you quickly some conclusion and outlook. The conclusions, what I want you to take away from this talk is that the heterotic G2 system is a source of interesting problems in string geometry. Hopefully I didn't obscure this too much, but I guess maybe I didn't talk about it a lot, but finding these solutions is only the beginning of the thing. You can wonder what is the moduli space of these solutions? How can I deform these solutions? There is a lot of interesting problems out there to be studied. And it's a natural occurrence of G2 instantons, for example. So in the same way that the Hall-Strominger system has, we're beginning to understand how important it is to construct certain geometries with torsion. This is a G2 analog of that. So there's a lot of interesting string geometry problems associated to this. Another takeaway is that it's hard. It's hard to find explicit solutions. But when you have a reduced structure on the compact manifold, then you can actually hope to do something here. And I think it's something that we see again and again in the literature, that it seems that when you have some nice symmetries in your problem, then you can do something. And more about what we actually achieved, we found some new solutions on this degenerate 3 alpha delta Sacchi manifold. With this ADS3 spacetime, which is interesting. There are not that many solutions of this type. And yeah, I think maybe something that I like to highlight is that actually this required a good understanding of the geometry. I feel like this project in particular is a very good example of what you can do when you join forces with other people, because when I arrived at Hamburg, I just sit on my desk and in front of me was Leander, who was an expert on these 3 alpha delta Sacchi manifolds. I have been working on these things on my PhD, and yes, we joined forces and we were able to find all these solutions. So a nice example of, and without a good understanding of the geometry underlying this, it would have been impossible to guess what were the right connections to choose and so on. And let me just very quickly tell you, or flash at you some future directions. We've been trying to generalize these solutions and think a bit about different G2 structures, G2 instantons, even extend this to other manifolds with parallel skew torsion, because this was very important for us. As I said, you can try to study a moduli space. You can try to search for T-dual solutions. Also look at some, from more physics side of things, try to understand this solution from a worldsheet perspective. Think of holography or Swampland conjectures. There's a lot of stuff to be explored yet, and hopefully I've motivated some of you to look into this kind of problem, which I think is very, very fun and very interesting. So yeah, thank you very much for your time. Happy to answer more questions if you have them.
Thank you.
Maybe can I ask, so in this, so you determined alpha prime to be inversely proportional to alpha, right?
Right. Yes.
In the degenerate family. So small alpha prime corresponds to very big alpha. So
yes.
Is something interesting happening in that limit of the degenerate case?
Yeah, absolutely. So So small alpha prime, yeah. So there's a couple of things to be said here. You're absolutely right. The solutions we found, or to have small alpha prime, you need big alpha. And if you trace back what big alpha means, and I hope I say this right because I always say it the other way around. Alpha is related to, well, maybe I don't need to actually scroll, but yeah, let me scroll to this diagram that I had here, right? So if you're going to a big alpha and you're going in this limit, and because we are in the degenerate case, and because of how alpha works, it's telling you something about the size of the fibers of this bundle. If you want you have like a T3, you can think of it as T3 vibration over a bundle, and this is telling you something about the scaling of your fibers. So what is happening in this limit is something that somehow your fibers are like blowing up. You take a limit where your fibers are blowing up, but also we cannot see it. Yeah, we can see it here. Tau zero, if you remember, it's related to the curvature of your anti-de Sitter space. Delta is equal to 0. So what is happening is that your ADS3 radius is also blowing up some sense, which means that you're going to kind of a degenerate limit. It's kind of so everything is well defined when you go to this alpha prime tends to 0 limit, but sometimes in the limit you would have a singularity. So you don't end up, if I remember correctly, what happens is that because two things could happen, that this anti-de Sitter free space could become just a Minkowski space, or it could become singular. In our solutions, it becomes singular. And yeah, I don't quite fully understand what's at work behind this. What is happening is just that to solve the equations, that's how they work. I think somehow what it's telling you is that, yeah, this limit is kind of a degenerate limit. Yeah, but it's an interesting behavior to observe. It's one of the first things that we looked into, what was happening in that case. Because in different cases, you have different things. In the literature, there are different examples. Different limits are achieved. Yeah.
Thank you.
I wonder, could you go back to the slide with the canonical connection for 3 alpha delta society?
Yes. This one, the family, or the one?
No, I think it was.
What I was saying here.
This is, I think, what I meant. So yeah, I guess I wonder what is the distinction you're making. You're saying what, that a 3 alpha delta independently has some canonical connection,
right? Yes. So I guess what I'm saying here, so 3 alpha delta is something that is defined in 2n plus 3 dimensions. So it doesn't have to be in 7 dimensions. You can think of 3 alpha delta in any 2n plus 3 dimensions. And it so happens that when you take 2n plus 3 equals 7, these canonical connections agrees with the characteristic G2 connection.
Oh, okay.
So what is happening, and sorry, I should have absolutely said this. I don't know why I didn't write it, but what is happening is that this canonical connection has holonomy SPn, SP1. So in the G2 case, what is happening is that this G2 connection actually has reduced holonomy. That's the title of the talk, actually. So this characteristic G2 connection secretly has holonomy SP1, SP1. It has it's a bit reduced. It's not reduced all the way to SU2, but it's reduced a little bit. And it's actually reduced to a very interesting middle case because, in this diagram, and now I'm going to talk a bit physics. If you have a connection, if your characteristic connection had actually holonomy SU3, then you have more supersymmetries preserved secretly. What is happening is that secretly you are solving something closer to the Hall-Strominger system, something more 6-dimensional. And the same happens with SU2. You will have more supersymmetries preserved. But because it reduces to the SP1, SP1, it still preserves minimal supersymmetry. So somehow it's like a sweet spot where you have a reduced structure, a reduced autonomy of your connection, but you're not reducing it so much that you have more supersymmetry. I don't know. And I think it's an interesting niche case in this diagram of inclusion that so happens. So that is the magic of these spaces. And in 7 dimensions, it so happens that the G2 connection reduces to this SPN SP1. In this case, SP1 SP1 connection. Yeah. But to answer your question, like the point I was making is that this connection that is defined in general for any dimension in 7 dimensions, they happen to agree.
Mhm. All right, any other questions? Okay, let's thank Mateo again, and I'll see you guys next week.
Yeah. Thank you very much.